So now that we've learned these basic reactions, as we said, all of the examples that we've done were on unsubstituted aromatic rings. But what happens if we already have a substituent on there? How will that affect what takes place in the reaction? And it's going to have an effect in two different ways. A substituent that's already on there can affect in terms of where the new substituent goes, and it also affects how reactive the aromatic ring is. So we'll start by talking about reactivity. And this is relatively straightforward. Given that the aromatic ring is functioning as a nucleophile, increasing the electron density in the aromatic ring makes it more reactive, whereas taking electron density away should make it less reactive. Or in other words, electron donating groups will activate the ring and it becomes a better nucleophile. On the other hand, electron withdrawing groups will deactivate the ring and make it into a worse nucleophile. And so we can see that illustrated here with just some relative rates. Looking at a group such as a nitro group, which is strongly electron withdrawing, chlorine, which is withdrawing, hydrogen, and then an OH, which is an electron donating group. So if we define our H as sort of our benchmark, an electron donating group like an OH group will make that aromatic ring react on average about 1,000 times faster. Whereas, putting a chlorine on the aromatic ring, chlorine is electron withdrawing, and it'll slow down the rate of that reaction by almost a factor of 100. A strongly electron withdrawing group, like a nitro group, almost 1,000,000,000 times slower. So the identity of whatever group we put onto the aromatic ring has a significant impact on how quickly, or in some cases, whether the ring will react at all. What about the orientation? In other words, where does a new substituent go relative to an old one? So we have three types of categories that we can divide our substituents into. We have ortho-para activators, ortho-para deactivators, and meta deactivators. So the activator or deactivator piece is whether this group is making the ring more or less reactive. And then our other part of the description is where that substituent's going to go. Is it going to go ortho-para or is it going to go meta? So examples of ortho-para activators include most carbon groups, but especially alkyl and aryl groups, alcohols, ethers, and amines. The ortho-para deactivators, that's kind of a special category and includes the halogens. And the meta deactivators are things like nitriles, carbonyls, nitro groups, and ammonium groups. So why is it that each one of these groups has this kind of effect on reactivity? So let's start by looking at an alkyl group. So I'll do this with a methyl just for simplicity, but this could literally be any alkyl group on there we wanted. And we're going to look at the sigma complex for the ortho substitution, meta, and para. So if we substitute ortho, substituent here, and note, it doesn't really matter what the reaction is. It matters what the substituents that are already on there are. And with each one of these, we're going to draw out the resonance structures of the sigma complex. So we should have 3 resonance structures in each case. So those are our 3 resonance structures for ortho. For meta, we're going to get a slightly different set of resonance structures. Oops, let's fix that one. And finally, there. And what about for para? And you may notice that the para ones actually have a fair amount of similarity to the ortho ones. All right, so there we have it. So why is it that we get ortho and para substituents from something like an alkyl group? Well, we want to very carefully draw our attention to 2 of these resonance structures, and I'm going to highlight them in yellow. So what is it that's special about these 2 resonance structures that I've highlighted? So every other resonance structure on this page, it has the carbocation in a secondary position. These 2 are tertiary. We know that tertiary cations are more stable than secondary cations. So what happens here is that the sigma complex for ortho and para ends up being more stable. And typically we know that if an intermediate like that is more stable, then that likely means that the activation energy to get to that intermediate is also going to be lower. So again, the primary and the ortho and para substitution positions both give us a tertiary carbocation, where all 3 resonance forms for meta are secondary. Now, for groups that are more resonance donors or resonance acceptors, we have to go through a similar argument, but it's actually a little bit simpler. Because we don't have to look at the resonance of the sigma complex. We can instead look at the resonance of the original starting material. So for example here with phenol, we can draw a series of resonance structures where the oxygen donates its lone pair into the aromatic ring. And we can continue to push those electrons around the ring. And we should start to notice a pattern here. What is that pattern? Well, we have a negative charge because of the lone pair oxygen. That negative charge is sometimes through resonance at the ortho position and sometimes at the para position. What that means is we have higher electron density at the ortho para positions compared to the meta position. And that means that our ortho para positions are going to be more nucleophilic. Now, what's going on with the halogens? Well, the halogens, we've said all along through this course that they don't donate by resonance. Well, here's an exception. They're still not thrilled to be donating by resonance, but in the aromatic ring, they will behave a lot like the phenol that we just talked about did. Now, the halogens being so electronegative don't really want to do this, and so they don't do as good a job of donating. So overall, the ring is still deactivated compared to the phenol, but there is an increase in reactivity at the ortho and para positions as well. What about some of the groups that we designated as meta-directors? And we could draw this type of set of resonance structures for any of them. I'm going to do the carbonyl here because it's the most common, but this would apply to any of the groups that we've mentioned. We know with a carbonyl we can always draw a resonance structure that pushes the electrons up onto oxygen. In fact, the set of resonance structures I'm going to draw here shouldn't be anything new to us. We've been looking at resonance structures like this since the first day of Organic 1. So once we have that positive charge next to the aromatic ring, we know we can draw a set of resonance structures that will distribute that positive charge all around the aromatic ring. And so it's kind of like what we saw a few minutes ago for, say, phenol, where phenol donated its electrons and put negative charges through resonance at the ortho and para positions. Well, this type of electron withdrawing group is doing the opposite. It's giving lower electron density at the ortho para positions. And so because it's giving us lower electron density at ortho para positions, it makes the ortho and para positions less reactive, and so these groups will prefer to substitute meta. Now, once we've got all this down, what really starts to complicate things is what happens now if we have multiple substituents already on the aromatic ring. So not just one. One is straightforward. If we know what the group is, we know if it's electron donating or withdrawing, and then we can make the assessment, is it ortho para or is it meta? But what if there's two groups to account for? Well, sometimes that's not a problem, such as this situation. Let's say we're going to do a bromination here. Well, the nitro group, that's an electron withdrawing group. Electron withdrawing groups, with the exception of halogens, want new groups to go meta. So the nitro is going to direct new substituents to one of those positions. The methyl group is an ortho para director, and so it's going to direct new substituents here, here, and in theory here, but it can't put a new substituent where the nitro group is because there's already one there. So these two groups reinforce each other. And so it's then, easy to make the assessment that a bromine is going to go in a position that's ortho to the methyl and meta to the nitro group. Where this becomes harder is when we have two groups that fight each other. Such as this situation. So the amine, we know that that's an ortho para director, and we don't have to worry about the para position because there's already a substituent there. But that methyl group down at the bottom is also an ortho para director. And unfortunately, the ortho or para positions of those two groups are not the same spots. And so basically this becomes a case of one group wins. Which group wins? Well, typically it's the group that has the stronger effect. Here we have an amine group. The amine is a resonance donor, whereas the methyl is just an inductive donor, and we know that resonance usually trumps induction, and so we end up with the bromine ortho to the amine and not ortho to the methyl group.